We're going to be looking at complex numbers today. So we want you to be able to simplify square roots and perform operations with those and with what are called imaginary numbers that we'll be looking at, and do any type of operations with these complex numbers. So the first thing we're going to look at is how to simplify roots or radicals. Two properties that we are going to be looking at over here is if you have two numbers being multiplied under a square root or radical sign, that is the same as taking the square root of the first number times the square root of the second number. An example of that would be if we had square root of 12. Okay, two numbers we know that multiply to be 12 are 4 times 3. So our property over there says that that is the same as square root of 4 times square root of 3. Now, square root of 3 doesn't simplify nice, but square root of 4 does. We know square root of 4 is equal to 2. And so another way of writing square root of 12 is 2 square roots of 3. And that's the type of thing we're going to be looking at today, is simplifying from here over to this one. Those both are equal to the same value. If you look on your calculator and do both of them, you should get the exact same thing. So if we type both those in, so square root of 12 equals this. Okay, if we do 2 square roots of 3, it's the same value, it's just written differently. Okay, but rather than doing that decimal number, if we want exact answer, we keep it as 2 square roots of 3. Same thing is true if you're dividing that. If you're dividing two numbers, A and B, under a square root, that's same as doing square root of the top number divided by square root of the bottom number. So an example of that would be, let's say you're taking the square root of 3/4. Well, that's the same as square root of 3 over square root of 4. And from before, we know square root of 3 doesn't simplify, but square root of 4 does. Square root of 4 is the same as 2. So another way of writing square root of 3/4 would be square root of 3 over 2. Okay. So that is what we're looking at with those types of problems. So now what we're going to do is look at what type of numbers should we be looking at when we're simplifying those square roots. We're looking for what are called perfect square numbers. Those are numbers where if you multiply the same number with itself, you get a perfect square. So like 2 times 2, or 2 squared, is 4. 3 times 3 is 9. 9 is a perfect square. 4 times 4 is 16. 25, 36, 49. All these numbers are perfect square numbers. Those are the numbers you want to try to see. Do we have any types of these numbers under our square root sign? Because then we can simplify them. Okay, so let's look at, on your note sheet, 1A here. We want to simplify that square root. So our goal is not to type in square root of 50 and write it as a decimal number. Our goal is to try to find any perfect square numbers in square root of 50 and write it as a simplified radical. So 50, we want to look. Do any of these numbers over here, our perfect square numbers, go into 50? Well, I think pretty quickly you can see 25 does go into 50 2 times. So what we're going to do then is write this as 25 times 2. Our property says then we can split this into 2 square roots as square root of 25 times square root of 2. Then simplify the perfect square one. Square root of 25 is equal to 5, because 5 times 5 is 25. So another way of writing square root of 50 is 5 square roots of 2. That's a simplified radical. All right, let's try B here, 45. What's a perfect square that goes into that one? Well, we know it's not going to be any of these ones that are bigger than 45. It's got to be one that's lower. 36 doesn't. 25 doesn't go in there. 16 doesn't. I think 9 does. So we want to put 9, or see what 9 times what goes into 45. 9 times 5 goes into 45. So we can split those into 2 those two square roots. Square root of 5 doesn't simplify, but square root of 9 does. Square root of 9 is the same as 3. So we can write this as 3 square roots of 5. That's simplified radical 4. All right, why don't you pause the video, see if you can do C here on your own and see what you get. All right, let's check it out. 128, looking for a perfect square that goes in there. Now there's a couple. 4 does go in there. 16 does, and actually 64 does. So that one has a couple of them. Anytime you have more than one, try to go with the biggest one and it'll get you to the answer the quickest. So I'll show you probably the quickest way of doing it and then maybe another way of doing this one if you didn't quite get the same answer. But if you take 128 and divide it by 2, you do get 64. So 128 is the same as 64 times 2. So we can write this as square root of 64 times square root of 2. And square root of 64 is 8 square roots of 2. That's the most simplified way to write this answer. Now, let's say you had picked a different one. Let's say you had maybe picked like 4. Okay? 4 does go into 128. You do 128 divided by 4. You get 32. So let's say you had did that right away and you had written this as square root of 4 times 32. Well, that gives you this. And that would have given you this answer. So if you got to this answer, it's not that you're wrong. It's just that you can go farther. 32 still has numbers that go into it. 16 is a number that goes into 32. So if you do that again now, split this up as 16 times 2. Okay, so now you got 2 times square root of 16 times square root of 2. Square root of 16 we know is 4. And now if you multiply 2 and 4, you get the same answer of 8 square roots of 2. So either way you do it, if you keep simplifying, you should be able to get to that 8 square root of 2 answer. It's just this way is a little more work than if you find the biggest perfect square right away. All right, let's look at D. Square root of x squared. Okay, when we're doing these problems, we've done some of these before. Like we were able to simplify in this one square root of 16. The reason we were able to simplify square root of 16 is 16 is a perfect square. 16 is the same as 4 squared. Okay, and the answer of that comes out to be 4. Square root of 16 is 4. So anytime you have a square root and a square, those are opposites of each other. It's really like they cancel each other out, and what you're left with is 4. So if you're taking the square root of x squared, that would be equal to x. The square root and the power of 2 cancel each other out. So anytime you have that, where you have square root and squared, those are opposites of each other. Let's try some problems then where we start throwing some variables in with it. Okay, so on letter E, okay, let's go through and do each one. Square root of 25. Square root of 25 would be 5. That is a perfect square. It's on our list over here. Okay, square root of x squared, we just had that. Square root of x squared is x. Okay, now what's square root of y to the 4th? Okay, so we got to think, what's being squared there? What times what to equal x to the 4th? Well, that would be the same thing as we have x to the 4th. Another way of writing that is y squared times y squared. So we could write that as square root of y squared times another square root of y squared. Well, what's square root of y squared? That's the same as that square root of x squared we had before. That would be y. That would be y. Y times y is y squared. So y squared would be the answer. Now, is there a quicker way of getting from here to here? Yeah, it's basically when you're doing this, kind of a quick cheat method to do it is to take the power and just divide it by 2. If you take the power and divide by 2, you get the same thing there. So that's kind of a quicker way of getting to that when you're doing it with variables. Okay, let's try one more here. This one, square root of x squared. Okay, anytime you got one of these and you can do simplifying first. If we got 2 x's on top here, which x squared is, and we got 1 on bottom. Okay, let's cancel out. If you got 1 on top, 1 on bottom, we can cancel one of these out. So what's left here is just square root of x. Square root of x we can't simplify if there's no power there, so that would just be the answer with this one is square root of x. Let's look at a few more fraction ones. So this is another fraction one. Okay, 11 does not go into 49, so then we want to go back to our property. Our property says we can write that as square root of the top number over square root of the bottom number. Square root of 11, 11's not on our list, and also the two numbers on here less than 11 don't go into 11, so we can't do anything with the top. 49 though is on our list. Square root of 49 is 7. 7 times 7 is 49. There would be the simplified answer for G. Okay, let's look at H. H, again, do the same, or look first, is there any number that would go into both those? I don't think there is. There's no number that goes into both 32 and 81. So write it as square root of 32, square root of 81. Now, let's start with the bottom because that's a little easier. 81's on our list. That is a perfect square. That's going to be 9. 9 times 9 is 81. On the top, 32 is not on our list. But do any of these numbers smaller than 32 go into that? 25 doesn't go into 32. 16 does. So then you still want to simplify this. This would be same as square root of 16. And 16 times 2 is 32, so square root of 2. And then we know square root of 16 is 4. So this would be the simplified way of writing that one. All right, last one, I. Look again, is there any simplifying you can do? Does 8 go into 32? Yeah, 8 goes into 32 4 times. Okay, so 8 goes into 8 once, goes into this 4 times, so this would be the same as 4x over 1. If something's over 1, you don't need to write the over 1 part. So now our goal is just to simplify what's square root of 4x. Well, if you're multiplying two numbers that have the same square root, we could write that as square root of 4 times square root of x. Square root of x doesn't simplify, but square root of 4 sure does. That's 2. So the answer would be 2 square roots of x. All right, so hopefully you kind of got an idea now of simplifying with roots or square roots a little bit here. When you're solving these problems out and you have x squared in it, because we know x squared and square root are the opposites of each other, we can solve. Okay, remember looking back before, we looked at square root and power 2 are opposites of each other. So we can use that to help us solve anything that has an x squared as part of it. So we are going to be able to solve a problem like number 2 here out by actually going through and solving this problem. So let's solve for x. We could add 25 to both sides. That cancels out. Now we got x squared equals 25. We can undo our power 2 by taking the square root. Now here's the thing, when you do that, when you take square root, not only is it the positive answer, but there's also a negative number answer that should also work when doing this. So you got to write it as plus or minus the square root of 25. So x is going to equal the positive and negative result of what we get when we take square root of 25. And that would mean there's two answers on this one. It would be plus or minus 5, because square root of 25 is 5. So both 5 is an answer and negative 5 is an answer. There's two answers that make this true. Because if you square 5, that's 25, and 25 minus 25 is 0. But also negative 5. If you do negative 5 and square it, that's also 25. 25 minus 25 is 0 here. We get the same thing. Okay, so you got to remember to put the plus minus part on there. I know you did that a lot in geometry last year, and you guys always just wrote the positive answer. Well, when you're dealing with geometry, a lot of times you're dealing with how long something is. you can't really use the negative one. So you guys were just answering with the positive, but really there is a negative answer too. All right, so let's try like B. Same thing. Only one x. We should be able to solve for it. Add 45 to both sides. Now we got 2x squared equals 98. Get rid of the 2. Divide by it, and we got x squared equals 49. And now to solve this, we can take square root. X is going to be plus or minus the square root of 49, which means we got two answers, positive and negative 7. So plus or minus 7 would be the answer. Okay, let's look at C. C is the same type of problem, a little bit different in that it's not just x being squared anymore. There's a 2 here too, but the steps are still the same. Start by adding 12. Okay, so now you got x plus 2 squared equals 25. Okay, now to undo power 2, we want to square root. Make sure you put the plus or minus with it. So now this side, that cancels out with the power, so it's just going to be x plus 2. And on the other side, we got plus or minus 5. Okay, now to finish, okay, we almost want to split this into two problems here. So we know that x plus 2 could equal positive 5, or x plus 2 could equal negative 5. So now solve both of them out and get the two answers. Both sides we're going to subtract 2 to get our two solutions here. So one solution is going to be 3. The other one is negative 7. Both of these two numbers should make that problem work on the top. All right, let's look at D. Looks like another problem pretty similar, so let's try this one. We need minus 48 to start with. That cancels. I get 3x squared equals negative 48. Looks like we want to divide by 3. That cancels, and I get x squared equals, and if you do that, you get negative 16. Now take the square root. So you're going to get plus or minus the square root of negative 16. And so is the answer then 4 and negative 4? Ooh, hold on. Let's go to our calculator. Can we do square root of negative 16? Can you do square roots of negative numbers? Ooh, nope. You get a non-real answer. Now, the reason that is square roots, you can't do square roots of negatives because there's no number that can multiply to itself to equal 16. As long as, or as far as you guys have worked with, there isn't. Now, there is a way to do this, and this is the other part of the lesson that we're going to be looking at. A French mathematician back in the 1600s looked at, could we still do a problem like that? So what he said is, let's come up with a number where if you square it, it equals negative 1, okay? And so what he used is the letter I. I don't know why he picked I, but he said I squared is going to equal negative 1. What that means is if we were to take the square root of both of these sides here, that I would be equal to the square root of negative 1. So he came up with a variable, and the reason he used I, it wasn't just random, it's because I, he's going to call an imaginary number. Okay, that's why sometimes we've said there's real numbers, and the reason that we call things real is that there is some numbers called imaginary numbers. Now, when he started doing this, there wasn't a ton of application for it, but later when people started working with electricity, they found out that imaginary numbers actually do play a part in like electricity and a lot of stuff with circuits, and it's very useful, and we won't have all the technology we did today without these imaginary numbers. So we can still solve if we get something with a square root of negative. Here's how it works. If we are solving, say, this problem right here, very similar to the ones we were just doing, we would subtract 2. We'd get 2x squared equals negative 2. We'd divide by 2. And we get x squared equals negative 1. we can now square root both sides. Okay, so we got x equals plus or minus the square root of -1. Well, square root of -1, that's the same as I, our imaginary number. So what we're going to say now is that x equals plus or minus I being the imaginary number. And for now, we'll just go with that. There is, like I said, some application that we'll be using later with something along with I. So let's go back. This problem that we were just doing D, we can actually solve it out then. So what you can do is anytime you have a negative inside your square root, that's going to become I. So negative in the square root, that becomes I. So what we can do is now write this as plus or minus I. And now that we take the negative out, it's only square root of 16. Well, we can do square root of 16 now. Square root of 16 is 4. So we would say that the answer for this one is plus or minus 4I, 4 times I. That would be the solution to this one. It has two imaginary answers. Okay, so how does all imaginary numbers work in with all this other stuff we've talked about? Well, we've talked about real numbers. Those are all basically the numbers you worked with up until this year. And there's two types that we looked at. There is rational numbers, and there's irrational numbers. And irrational numbers, you know a couple of those. Those are like pi, and we looked at there's one that you'll look at later in the year, the natural number e. Any square roots that you can't simplify, such as square root of 2, they're decimal numbers that just keep going on forever without repeating. Those are called irrational numbers. Rational numbers would be anything else that is a decimal number that stops or that repeats itself. So like 5/7 or something like that would be a, write these, 5/7 would be an example because that is a number we know exactly what that equals. It's 5/7. Or like 1/3 is a rational number. If you simplify that out, it's like 0.3 repeating. That's a number that can be turned into a fraction. These ones can't be turned into a fraction. Now within rational numbers, we have some more numbers. There's the set of integers. Integers are numbers that are positive or negative whole numbers. So -3, -2, -1, 0, 1, 2, 3. Those are all whole numbers, and we could keep going in either direction here. Those are integers. Within integers, there's some groups called whole numbers. Okay, those would just be all our positive whole numbers, including 0. And then with that, we have a group called natural, or our counting numbers. That'd be the same group, just not counting 0. Just your counting numbers, 1, 2, 3, 4, etc. Okay, so you've worked with mostly the ones in this circle right here is the one you've kind of worked on the most. We've started working some with the irrational numbers last year in geometry, and this year. The new one, though, that we just added now is imaginary numbers. Okay, imaginary numbers have I in it. So like 5I, imaginary 5, that would be one. They can be negative too, so you could have like -7I. Any square roots you have that have a negative underneath would also be imaginary. Now, if we group together real numbers and imaginary numbers, they do have a name. They're called complex numbers. That was the title of this notes. So complex numbers have both a real and an imaginary part. So you might see something like this, 2 plus 3i. That's a complex number because it has a real and an imaginary part. Here's another example, -1 minus 7i. That is a complex number. So when we say complex numbers, it means there's a real and an imaginary part. Okay, well, let's work with some of these imaginary numbers here and see if we can't solve some of them out. So on the first one here, we're looking at what is square root of -18. So the first thing we want to do, if you have square root of a negative, pull that negative out, and that's going to change to an I. So this would be equal to I, and now it's just square root of 18. Okay, well, what is square root of 18? Is that one of the numbers on our perfect square list? Nope. So let's look at, did any of them less than that go into it? Nope, 16 doesn't go into it. Does 9 go into 18? Yep. So now we're going to, just like we did before, change this to 9 times 2 is 18. Square root of 9 simplifies, so we could write this as I times square root of 3 times square root of 2. That would be an okay answer. That's correct. Most of the time, though, I is written after any whole numbers, so usually you'd see it written like this. Not a big deal. I would take either answer. They're saying the same thing. It doesn't really matter to the order that you multiply things. All right, let's try B. Again, we see a negative. So any negatives, we're going to take that outside of that and turn it into an I. So now it would be I square root of 125x to the 5th. Okay, so do any of these perfect square numbers go into 125? Well, 25 certainly does. So if you take 125 and divide by 25, you find out that 25 times 5 is 125. Okay, but then we still got this x to the 5th part. Okay, now remember our little cheat way before is to take that number and divide by 2. The problem is if you take 5 divided by 2, it's not a whole number, you get 2.5. So what you want to do on this then is if you just divide it by 2, take the whole number part of that, 2. We can take 2 of these x's out. So what we want to do, just like we did here, is splitting this into 2. We're going to split x to the 5th into 2. We're going to say it's x to the 4th times x to the 1st. Okay, because 4 and 1, we still got 5 x's here. It's just that we've separated them. So now we want to simplify the ones that we can. This simplifies. That's 5. This simplifies. That's going to be x squared. That's the 2 I was talking about. Okay, these other 2 don't simplify. Square root of 5 is going to be a messy number, and square root of x doesn't simplify either. So if they don't simplify, then just leave them in that form. So we're just going to leave it as square root of 5, and we're just going to leave it as square root of x. And we got to make sure we have our I with us. Okay, so now last thing we do is just try to write this a little bit nicer. Usually whole numbers are written first. Okay, and then if there is a variable, usually that's written second. We want to get our I in there. Okay, now the last part, we got these 2 square roots. Rather than writing 2 square roots, let's just combine them back into 1. We can do that and just write it as square root of 5x. That is how we would try to simplify that one. Okay, it might look actually a little bit messier, but you can work with stuff outside of a square root and combine them and do other stuff with them once you do that. All right, let's keep going on your notes. C, okay, on this one, square root of negative 10 times square root of negative 15. Okay, now something interesting is going to happen here. Both of these are imaginary numbers in that we got square root of a negative. So let's do like we did before, turn that and that into I. Okay, so now we got I square root of 10 times I square root of 15. Okay, well let's multiply this now. We got I times another I, that's going to be I squared. Neither 10 nor 15, okay, if we look at either of those, 9 and 4 don't go in either of those. So let's multiply those together too. That's going to be square root of 150. All right, now from first glance, that might look like we can't do anything else with it, but actually we can. 150 now, if you look over here, there is a perfect square that goes into 150, 25. 25 goes in that 6 times. So we can write this as square root of 25 times 6. And we know 25 is going to simplify to 5. Square root of 6. Now what about this I squared stuff? Well, if you remember back, okay, we had talked about this I stuff. And originally what we said was this Descartes guy said I squared is equal to -1. Do we have an I squared in our problem? Yes, we do. So we know we can change I squared. Anytime we have I squared, that's going to be the same as -1. So we can change that into a -1. And then now that we have -1 times 5, the answer is going to be -5 square root of 6. So the big deal about this one is when you multiply two imaginary numbers, which we started with, both of these were imaginary. When you multiply two imaginary numbers, look at the result. Was the result an imaginary number? No, the result was a real number. And that's why there is some applications of this, because when you multiply two negative ones, you actually get, or two imaginary ones, you actually get a real number. Let's look at another one similar to this. -2i times 7i. All right, same thing. It looks like two imaginary numbers. Last time when we multiplied two imaginaries, we got a real answer. Let's see if that happens again. We multiply these two numbers, we get -14. I times I, that's I squared. What do we know about I squared again? We know it's the same as -1. Well, -14 times -1 is +14. A real answer. So anytime you multiply imaginary numbers to imaginary numbers, you get a real solution. All right, let's work with some complex numbers. Okay, complex means we have both a real part, 6, and an imaginary part, -4i. What if we had that with another complex number with a real and imaginary part? Well, what you do with this is you just add the same parts together. We're going to add together the 6 and the 1, the two real parts. That's going to equal 7. Then we're going to add together the two imaginary parts. What's -4i plus 3i? Oh, that would be -1i. And that would be the answer. We can't subtract this and get like 6 or 6i because they're not like terms. So our answer is the complex number 7 minus 1i. You don't need to write the 1 there. You could just write it as 7 minus i2. Either one would be fine. All right, let's try another one. This one we are subtracting two complex numbers. Now subtraction's a little bit tougher. What you got to see here is if we're subtracting, we're not only subtracting this real part, we're also subtracting this imaginary part. So it's almost like when you're subtracting and there's a parentheses, you got to distribute that negative sign. So really what we end up with here is minus a negative, that's going to turn into +1. And then minus 2i at the end. Now if we combine the real and imaginary parts, we'd get -1 for the real part. 5 minus 2i is going to be 3i for the imaginary part. That would be the answer to this one. All right, here's a little joke on this one. The imaginary number is talking to pi, and I says be rational, and then pi says get real. Okay, it's kind of a play on our little Venn diagram chart we had before, because pi is a irrational number and I is a imaginary number, not a real number, so they're kind of making fun of each other. That's a dorky math joke there. All right, some more stuff to do with imaginary and complex numbers. On this one, see, this is multiplication. This is just that FOIL stuff that you guys have done before. Multiply first, outside, inside, and last. So if you multiply this out, 6 times 6, that's going to be 36. Now let's multiply our outside ones. That's going to be plus 6i. Multiply our inside ones. That's going to be minus 6i. And then finally, let's multiply our last ones. It's going to be negative because we got negative times a positive. I times I is I squared. Okay, now if you look, these two middle terms, 6i minus 6i, those end up equaling 0. Okay, then what's left now is 36 minus I squared. Now, again, from first glance, it looks like we're done with the problem because those aren't like terms. But what do we know about our old friend I squared here again? I squared is equal to negative 1. So we can write this as 36 minus negative 1. Well, minus the negative, that's going to turn into plus. The answer to this is 37. 37 is the answer to those. So multiplying those two complex numbers actually ended up getting us a whole number answer there. Now, if you look at the two things we multiplied up there, they were exactly the same. 6, 6, I. The only difference was the two symbols. One was negative, one was positive. When you multiply two things like that, that's called a conjugate. A conjugate is multiplying the same thing, like this one was 2x plus 5, 2x minus 5. Same thing, the only difference is the signs are different. Conjugates are going to come back again later. I just want to kind of bring that up, but that's called a conjugate. And you always get kind of a cool answer like this when you multiply by a conjugate. All right, let's try D. Same thing, we're going to multiply that through because we're timesing here. So multiply first ones, you get 6. Multiply outside ones, you get 3i. Inside ones would be 4i. And the last ones, you get plus 2. I times I is going to be I squared. Now let's simplify that. Now here the middle ones don't cancel, but we can add them together. That would be 7i plus 2. Here's our friend I squared again. We know I squared is the same as negative 1. So if we times that together, that's going to be negative 2. We can actually simplify this farther now because now there's more like terms. The final answer on this one is 4 plus 7i. That would be the complex answer. All right, very last problem. Here's an application, maybe using some geometry here. They say the base of a parallelogram is half of its height. If the area of the parallelogram is 18 inches, what's the length of the base and length of the height of the parallelogram? So just going back again to geometry, if you got a parallelogram, area is the base times the height. The height is that perpendicular height there. So we don't know what the base and height is, but we do know that the area is 18. So in our equation here, we can plug 18 in for A, the area. They do tell us something here, though. They say the base is half its height. Okay, the base is half the height. So what we can put in for B then is that the base is the same as half the height. So if we solve this equation out, we should be able to get to our answer. So we got 18 equals 1/2. If we multiply these two h's together, h times h, that's h squared. All right, well, let's keep going. This is being divided by 2. The opposite of dividing by 2 is to times both sides by 2. So on that side, it cancels out. We're just going to have h squared. On the other side, now we got 36. Okay, hopefully you see how to finish this one now. To undo our power of 2, square root. So we get plus or minus the square root of 36, which is plus or minus 6. So the height's either positive 6 or negative 6. This is a geometry one, so we're going to go with the positive one here of 6. So that means the height is 6, and that would be in inches. And then the base we know is half the height. That's what we talked about before. Base is half the height. So if we know the height is 6, that'd be half of 6, which is 3. So the base is 3, the height is 6. All right, try some of these out now on your own for the practice.